Hi, let's take a look at an example for a block on an incline. So what I'm going to do is I'll just pick some random masses here. I'm going to say that the mass of the block, which I'll just call M sub B, is equal to 5 kilograms. And I'll say that my angle here is 22 degrees. So let's figure out some of the important things that we're going to need to know. So the force of gravity, obviously, is going to be equal to mg. So that'll be 5 kilograms times 10. So the force of gravity is equal to 5 kilograms times 10 meters per second squared. And the units for this are newtons. So that's 50 newtons. And that's basically just the force of gravity down. But we really need to know the force of gravity in two other directions. We need to know the force of gravity in the perpendicular, right there, so that we can figure out what the normal force is, the force normal. And we need to know the force of gravity parallel to the incline, which will give us the force going down the incline. So the force of gravity that is perpendicular to the incline is going to be equal to mg times the cosine of theta, which is 22 degrees. And if I plug that into my calculator, so m is 5 times 10. So I have 5 times 10 times the cosine of 22 degrees. I end up with 46.359. So I'll call this 46.4 newtons. So that's my force of gravity in the perpendicular direction down, which means that my normal force is the same in the upward direction. So my force normal, and I'm going to put some bars around this. It doesn't really matter. You don't have to do that, but I'm doing that to say that the magnitude of this force is going to be equal to this force of gravity in the perpendicular direction. So the force normal is also 46.4 newtons. So that's the perpendicular force. Now, what about the force going down? Because if we look at our free body diagram, we have the normal force and we have the force of gravity. So here's our force of gravity and here's our normal force. So we should have a net force. Now this would not be on a free body diagram, but our net force really, we know, is going to be in this direction. That's our net force. So how do I solve for that? Well, that net force going down, if I just slide this down here, it's the opposite leg or the opposite end of our triangle from this angle theta. So that's our sine. So I'm going to start back up here and I'm going to say that the force of gravity parallel in that direction, parallel to the slope of the incline, is going to be equal to mg, that's the force of gravity down, times the sine of theta. So I'll just substitute in my numbers. I have my 5 kilograms. I have 10 meters per second squared for gravity. If we were doing a lab, we might use 9.8, closer to the real thing. But here we can approximate, times the sine of 22 degrees. Plug that into my calculator. 5 times 10 times sine of 22 degrees. And I end up with 18.7. So my force of gravity parallel is 18.7 newtons. So this is the force, the net force going down if there are no other forces involved. Now, what happens if I actually have a force of friction? If I have a force of friction, that would oppose the block sliding down, and it would be in this direction. So I could add that to my free body diagram. it would be in this direction, the force of friction. If the force of friction is preventing the block from sliding down, then that means it's equal to the force that makes the block want to slide down. It's just in the opposite direction. So the magnitude of the force of friction is equal to the magnitude of the force of gravity parallel. So it's equal to 18.7 newtons. So it's the same. If the block doesn't slide, the force that makes it want to slide must be opposed by an equal force of friction. So this is still the same answer. If I was given a force of friction, if I had a problem that said, suppose the force of friction is equal to 7 newtons, what's the net force down the hill or down the incline? Well, I would just take my force above here, my force that's of gravity parallel, my gravity parallel to the ramp, and I would say my net force is equal to the force of gravity parallel minus the force of friction. So it would just be equal to my 18.7 newtons minus, what did I say, 7 newtons. So it would just be 11.7 newtons if that was if my friction was given to me. If it's not given to me and I'm told that the block is not moving, well, then it has to be equal to the force that makes the block want to move. It can't be higher because friction can't pull the block up the hill. And if the block is not moving, it can't be lower, or else the block would slide down the hill. So it has to be exactly equal. Another condition where it can be exactly equal is if the block is already moving, but it's moving at constant velocity. In that case, the friction force is also equal to the force down the incline. Now, in your quiz, you will get a couple of other questions. Let's see if I can find a good eraser here. There are a couple of other kind of thought questions. One of the thought questions says, suppose that I have a spring scale. I'll draw a spring scale here with some markings on it and a little loop, and it's attached to a pole here, maybe a ring stand, and a string. And what is the force of tension? What is the force of tension? Well, we already found that the force of gravity parallel was equal to 18.7 newtons. That's the force of gravity making it want to slide down. So if the spring scale and the string are preventing it from sliding down, then guess what? The force of tension is just equal to that force right there. They have to be the same because it's not going down. In this case, instead of having friction to prevent it from going down, we are measuring the force going down, assuming that there isn't any friction, and we're just saying, what's the force that makes it want to go down? And instead of calculating it, we would read it off of our spring scale. What we're doing here is calculating and saying, this is what we would read on our spring scale if we did that. Another example that we could use is this one. Suppose that I have a pulley mounted here at the top of the device, and I have a string that goes over the top of the pulley and then hangs down, and on the other side I have a weight. So I've got a weight right here. If I'm told that the weight is preventing the block from sliding down the hill, then the force provided by the weight has to equal the tension force that would prevent it from going down the hill, which has to equal the force that would make it want to go down the hill. So basically the weight here has to provide a force equal to this tension force. So we can calculate the weight of this object, the force of weight of block number 2, or however we want to label that, is equal to this force. So then if I want to calculate the mass of that block, we know that force is equal to mass times gravity, and we're using gravity as 10, so force is equal to mass times 10 meters per second squared, which means if I plug in the force right here, whatever that happens to be, some number, I can divide it by 10, and I'll end up with the mass right there. So the mass will be smaller than this mass, because this mass, its gravity is entirely dedicated to tension on the string, whereas this mass here, only part of it is dedicated to the force on the string. Okay, so that should be enough to help you get on with these questions. And if you have any more questions, you can just shoot me an email.